yesterday you had lab. Everyone had lab. You did the calorimetry experiments. I hope it was fun. You did 3 experiments yesterday, all using the coffee cup calorimeter. And if you've been looking ahead, I've got 3 practice problems in the next 3 slides that basically take you through the same 3 experiments that you did yesterday. Because they're all using the coffee cup calorimeter, but the experiments were all slightly different. And each one was doing something a little bit different. So we're going to go over those again today and do some practice. So I hope you brought your calculators with you. Okay. And when we do that, I'm going to also emphasize what it is that's different between the 3 different experiments that you did, so that when you are faced with a similar problem, you'll know what to do. Because sometimes you add a mass here or you don't add a mass. Sometimes you need to keep track of the temperature change and whether it's positive or negative. You need to make sure that the sign usage is correct. All right, so today is going to be a review then of what we did in lecture on Monday and what you then did in lab yesterday. All right, so let's carry right along. So here's one example. In this case, we're dissolving sodium hydroxide in water. So this is the dissolution experiment. Dissolving something in water. And that has some energy component associated with it. Yesterday you dissolved was ammonium chloride. And which way did the temperature go? The water went down. It better have, I hope. Okay, because that reaction, right, when you dissolve ammonium chloride in water, it takes energy from the surroundings into the system. It's an endothermic reaction. Okay. Now this one is similar. In the second experiment that you did, you had to dissolve some sodium hydroxide in water. That one warmed up a little bit. That reaction is exothermic. So the actual experiment, the reaction is dissolving it in water. That gave off energy for the sodium hydroxide. When you did it for ammonium chloride, it took energy away from the surroundings. That's why the water got colder. In this example, the water is going to get hotter. And you can see that right here. The initial temperature is 20 degrees Celsius, and the final temperature is 32.7 degrees Celsius. So in this case, it's getting warmer, which means it's going to be exothermic. Meaning that in this case, the water of the calorimeter got warmer. That meant that the reaction gave off energy, right? The water gets warmer, which means that the reaction gave off the thermal energy. Okay, but now let's do the calculation. We know that we have this relationship that the energy, the thermal energy that we measure is equal to the mass of the water that's changing multiplied by the specific heat capacity of the water, because that's what the thermometer is in contact with. That's what's changing. Multiplied by the change in temperature, and that's going to be T final minus T initial. Now, in this case, though, we're dissolving the NaOH in the water. So we need both the mass of the water, which in this case was 50 grams of H2O. But in this case, we need to add the mass that we're dissolving, plus 2.5 grams of NaOH. So the total mass that the thermometer is going to be in contact with once that sodium hydroxide has dissolved is actually going to be 52.5. In this case, when you're dissolving a solid into the water that's in the calorimeter, you need to add the mass of what's being dissolved. Because in the end, you're going to have an aqueous solution. And that's what the thermometer is in contact with. And you're measuring, that's the surroundings. Because even though we're adding the mass here, it's all one aqueous solution. And it's a dilute aqueous solution. And so our assumption is right here, because it's a dilute aqueous solution, even though we know that there's some sodium hydroxide there, we're going to assume that the specific heat capacity of the water is still going to be our 4.184. Let's put a 4 up here. Joules per gram degree Celsius. So we can still assume that the specific heat capacity here is going to be 4.184 joules per gram degree Celsius. Now our delta T, we already know. Now by convention, that's T final minus T initial. Okay, so T final minus T initial is going to be 32.7 minus 20. So that's going to be 12.7 degrees Celsius. And that's positive. I'll put a positive sign here. That's our temperature change. Specific heat capacity is always going to be a positive value. The mass is always going to be a positive value. So this is going to give us a positive value for Q. Because Q, this is Q of the calorimeter that we're measuring. This is Q of the water in the calorimeter. The water is going to get warmer because the reaction is giving off energy to the surroundings. So if we keep track of T final minus T initial, we'll have the right sign on the temperature, and that will give you the right sign in the calorimeter. So if we do this math, what do we get? And we get a number that's in joules, right? The units here will cancel. Grams with grams, degrees Celsius with degrees Celsius. We're left with the units of joules. So this is going to equal 27, I'll just round this up to 2790 joules. That's how much energy, thermal energy, was taken up by the water in the calorimeter when we dissolved 2.5 grams of NaOH in 50 grams of water. Okay? But we want to calculate the enthalpy of dissolution. The enthalpy, remember, enthalpy is delta H. This is going to be the delta H of what we call dissolution. Dissolution. It's sometimes also called the delta H of solution. And you'll be seeing this more and more as we go on with the lectures. We're going to be defining delta H of the reaction. As I told you on Monday, that's going to be Q divided by the moles that were reacted. That's always going to be delta H. Now, delta H of the reaction here, let me write that a little more distinctly. Reaction is a general term. Any reaction that we're studying, it's going to be per mole of that reaction. If we're defining a specific kind of reaction, then it's going to be for 1 mole of that reaction. In this case, we're dissolving NaOH. So the delta H of dissolution is going to be the energy associated with dissolving 1 mole of that material in solution, because it's going to be per mole. Okay, so this is dissolving 1 mole of material. In this case, the material is NaOH. So we need to see how many moles of NaOH were actually dissolved here so we can calculate delta H of solution or dissolution. So we know how to do that. 2.5 grams. We need the molar mass of NaOH, which you can calculate it now. I hope you know how to calculate it. But let's just, sodium is 22.999 and oxygen is 15.999, and the hydrogen, that should give you 40.01 grams per mole. Right, that's the mass. Here, let's put all of our units in. That's moles of sodium hydroxide. Right, so there's 40.01 grams of NaOH in 1 mole of NaOH. That, of course, will tell me how many moles we have. 2.5 divided by 40.01. That's 0.0625 moles. So there's joules. That's how many joules of energy were produced when 0.0625 moles were dissolved. So we divide one by the other, we'll get joules per mole. Joules per 1 mole, right? 44.651 joules per mole. All right, that's a pretty large number. And remember that for delta H, that's reported in kilojoules per mole. So let's change that to kilojoules. We'll divide that by 1,000. That'll be 44.7 kilojoules per mole. That's the delta H of dissolution for sodium hydroxide based on this experiment. Okay, now that seems like it's a lot, 44.7 kilojoules per mole. You would expect if it produces that much energy when you dissolve sodium hydroxide in water, you might think, well, why didn't your solution get so hot when you did it yesterday in lab? And the answer is that you didn't dissolve 1 mole. But I think on average, you're probably only dissolving about 0.02 to 0.03 moles of NaOH, what you did yesterday. So you're only producing a fraction of that energy when you dissolved a fraction of a mole in water, okay? But this value, delta H of dissolution, it will always be 44.7 kilojoules per mole, regardless of how many moles you're dissolving. This is your conversion factor. It's something per something else. So you can use delta H as a conversion factor if you need to convert between energy and moles that were dissolved in this case. This is a very classic experiment, but in this case, you need to add the mass of what was dissolved because ultimately you're making an aqueous solution. Okay? Now, in the next example, you did this experiment. Although this is kind of wordy. I took this one out of the textbook. The textbook, much as I like it, tends to be kind of wordy with their problems. So let's just distill down what we're doing here. We're taking HCl and we're mixing it with NaOH, and you're doing a neutralization reaction. And this is exactly what you did yesterday. So let's just put the reaction up here. These are aqueous solutions. And what do we get when we mix an acid with the base? What are the two classic? Salt and water. In this case, the salt is the Na and the Cl, so that'll give us NaCl as the salt and H2O. This is a neutralization reaction. And what you did yesterday, you did this reaction yesterday. But yesterday, the HCl was in excess. And you measured the mass of sodium hydroxide that you dissolved in water. So you made the aqueous solution of sodium hydroxide. The aqueous solution of HCl was given to you, okay? And we did it that way so that you can calculate to 2 decimal places how many moles of sodium hydroxide were actually being reacted, okay? Because the balances can measure out to 2 decimal places. So you measured the mass of NaOH and then you made your aqueous solution. So in your experiment, NaOH was limited. When that limiting reagent runs out, the reaction stops. That's the calculation that you did yesterday. You figured out how much is going to react. There will be HCl left over, but that's not going to contribute to the energy that's released in this reaction. The energy stops being released once the reaction stops, when your NaOH runs out. In this example here, everything is perfectly stoichiometric. Nothing's going to be in excess. Nothing's going to run out. Well, they both run out at exactly the same time. And you can see that if we look at the moles that are actually being reacted. If you look at this reaction that I wrote up here, it's balanced. Okay, so let's take a look at how many moles we actually have that we're working with. We're taking 0.2 liters of a 0.2 molar solution in each case. Okay, so I'm just going to put this down here. 0.200 liters. That's how much we're taking. And the concentration is 0.200 moles per liter. And moles of HCl or moles of NaOH, it doesn't matter because these numbers are exactly the same. Let's put it in NaOH, it doesn't matter. I'll say HCl or NaOH. Either way, we're getting, what is that? 2 times 2 is 4, and we got point, so that's 0.04 moles. That's what's being reacted. And it's perfect, right? Nothing's in excess. This is all 1 to 1 to 1 to 1. So we're reacting basically 0.04 moles of HCl with 0.04 moles of NaOH. And you remember your stoichiometry, we're going to produce 0.04 moles of NaCl and 0.40 moles of H2O. Okay? All right, so let's go ahead and do the math then, because now it's pretty straightforward. We measure what's happening in the calorimeter. And in the calorimeter, we have a mass. But what is that mass? What's the mass of water in the calorimeter here? We are going to assume the density is 1 gram per milliliter. Now that's an assumption that you don't do in lab. In lab, you would have just taken it to the balance and measured it by subtraction. Okay, but we're not in the lab now. So I'm telling you, I would either give you the mass or you can assume it if you're told to with this density. So if it's 1 gram per milliliter, all right, how many milliliters are in 0.2 liters? 200 milliliters. So that's 200 grams. So how much is the mass of the calorimeter? It's 400 grams because we have 200 of the HCl and 200 of the NaOH aqueous solutions. All right, so this is going to be 200 grams plus 200 grams. So this is 400 grams of the aqueous solutions. They're both dilute aqueous solutions. So once again, we're going to assume the specific heat capacity of water, and you're told that assumption right here. So let's just put that in, 4.184 joules per gram degrees Celsius. And the delta T, what is the delta T? Well, the initial temperature is 22.15 degrees Celsius. Whoops. 0.15 degrees Celsius. And the final temperature, well, you're not told the final temperature, but you are told the equilibrium temperature, and you know that that's the final temperature. That's going to be 23.48. That's the final. So T final minus T initial. This didn't go up by much. Looks like it went up by positive 1.33 degrees Celsius. Okay, and that's the calculation, but that's Q for the calorimeter. Positive 2226 joules. That's thermal energy that was absorbed by the calorimeter because the water temperature increased. So what happened in the reaction? It gave off the same amount of energy because Q of the calorimeter is equal to negative Q of the reaction, or vice versa. So that means that Q of the reaction is negative 2226 joules. Is the reaction endothermic or exothermic? It's exothermic, right? The negative sign means that energy is leaving the system. That's our convention. So that's how much energy left the system when we reacted those specific amounts. So now let's calculate the delta H for that reaction. That's going to be that amount divided by the number of moles that were reacted. In this case, it's the same, right? So 0.04 moles. That's going to give us our delta H of this reaction. 55,647. That's joules per mole, but we want to report that in kilojoules. So that's going to be 55.6 kilojoules per mole, but it's negative, okay? Here, let's make that clearly an equal sign. It's negative because Q of the reaction is negative, okay? That's why your sign convention is really important. This reaction is an exothermic reaction. So when you're defining what delta H of that reaction is, you've got to have that negative sign. That's telling you that it's an exothermic reaction. Now you might think, well, wait a minute, but the problem we did before, when we dissolved the NaOH in the aqueous solution, that was also exothermic. So are we ignoring that here? Because In the previous problem, we were measuring the enthalpy related to the act of dissolving it in solution, okay? In this experiment, you're starting with the aqueous solution. So that earlier delta H, it's already happened. It's water under the bridge. Yes, there was energy associated with making those solutions, but now you're working with the aqueous solution. So the problem here is starting with the two aqueous solutions, and now what's the enthalpy related to mixing them together and the reaction that's happening. So now the reaction is not dissolving. The reaction is this reaction here. It's the neutralization, and it's all happening in aqueous solution. There's no solids in here anymore. That's why the mass, we're just taking the mass of the aqueous solutions now, and there we are assuming that the density of those aqueous solutions are the same as the density of water. So yes, those are assumptions, okay? But that's why we paid attention to the mass in the first problem, because that was part of the dissolving. In this problem, we're not taking into account the mass of the HCl or the mass of the NaOH that's in the aqueous solution. We're just assuming that that's now the same as the density of water, okay? So the reaction is still happening, but now the reaction are the ions that are already in solution are interacting with each other. There's still thermal energy associated with that interaction, and that's what we're measuring here. Okay, so it may seem like a subtle difference, but hopefully it's starting to sink in. All right, the last experiment that you did yesterday was measuring the specific heat capacity of the unknown block. Now in that one, we took our calorimeter. You had some mass in the calorimeter. In this experiment, the mass in the calorimeter is 50 grams. You're told it's 50 grams of H2O. And we're going to take our piece of gold here, let's say. It might not be gold. Let's say you think it's gold. So here, we'll color it in, right? Some unknown metal block. And you're told what the mass of that is, 25 grams. And you're going to heat it to 100 degrees Celsius or close to it. And then you put that in the water. And of course, you've got a thermometer in the water. And so you measure what the temperature change of that water is when they reach thermal equilibrium. So here's our metal block in here. And we talked about this the last time, and you did it yesterday, right? The metal block, you put it in water. If the initial temperature of the water is, what does it say here? The water was 19.3 degrees. And the metal block is 100 degrees Celsius. So we know that when you put the metal, the hot metal into the water, the metal is going to get cooler. And in the process, the water is going to warm up because the metal is giving off the thermal energy. The water is taking up the thermal energy. Now here, the thermometer is only in contact with the water. That's all you're measuring. So in this case, the mass of your calorimeter is just the mass of the water. You don't add the mass of the metal block that you put in there because you're not measuring that, and that's not dissolving into your solution. So it's not contributing at all to the mass of the calorimeter that you're measuring the temperature change in, okay? So in this case, you don't add the mass at all of the block. Now, of course, this temperature change will continue until both reach thermal equilibrium. And at thermal equilibrium, we have 27.1 degrees Celsius. So that means the final temperature of the metal block and the final temperature of the water will both be 27.1 degrees Celsius, right? So we're still going to use our principle that Q of the calorimeter is equal to minus Q of the reaction. In this case, the reaction is the metal giving off the heat. And in doing so, we're going to measure what the specific heat capacity is. How much heat does it give off relative to the mass that it was? So we can keep track of all these things. The Q of the calorimeter, right? That's just the water now in the calorimeter. That's going to be equal to the mass of the water. That was 50 grams of water. The specific heat capacity of water, 4.184 joules per gram degree Celsius. And the temperature change that the water experienced. Now the water's getting warmer. So T final is 27.1 degrees Celsius minus T initial, which is 19.3 degrees Celsius. 7.8. And it's a positive 7.8 degrees Celsius because we're paying attention to final minus initial. So we can calculate that's going to be some energy. 1,630. Should we round this? Well, technically, we would only round it to 3 sig figs because we're given only 3 here. Although I tend to not want to round to sig figs until you're done with the actual calculation. Although really, this is the end of the calculation. That's fine. Let's just carry some more. It's always a good idea to carry 1 or 2 more and then round in the very end. Although really, if we were paying attention to sig figs, this number would really just be 1630 if we're reporting it to 3 sig figs. All right, now that's a positive number. That's how much thermal energy was absorbed by the water, which has to be equal to the same amount of thermal energy that was given off by the metal block as it was cooling. All right, so Q of the cal is equal to minus Q of the reaction. That means minus Q of the reaction is going to be equal to the mass of the metal block, which is 25 grams, this was water, times the specific heat capacity of the metal block, which is what we're trying to calculate. So we don't know what that is yet. So that's going to be X joules per gram degree Celsius times the change in temperature that was experienced by the metal block. It's not going to be 7.8 degrees Celsius because it has a different specific heat capacity. It takes either a lot more or a lot less energy to have that metal experience a change of 1 degree Celsius than it does for 1 gram of water. So what was the temperature change experienced by the metal block? The final temperature was still 27.1 degrees Celsius, but the initial temperature in this example is 100 degrees. In your case, you would think it was 100 degrees, but you're going by whatever your laboratory thermometer says, which never reads 100 degrees when you're boiling water in lab. That's just because we're using really high-grade thermometers. All right, but we're not in lab, we're doing a exercise. So let's see, 100 minus 27.1 should be 71.9. Huh? 72.9, thank you. But it's negative 72.9 degrees Celsius because we're paying attention to final minus initial. But remember, X is always going to be positive. So because we're setting Q of cal to be equal to minus Q of the reaction, that wouldn't work if the temperature didn't give us a negative change in temperature. You see that? Because you could have solved this another way. By the way, the rest is just solving for X. Why don't we just finish that up and solve for X? So now we want to solve for X. We can just use this equation here in red. Because we know that negative 1631.8 is equal to 25x minus 72.9. So now X is equal to minus 1631.8 divided by 25 divided by minus 72.9. And now we'll have our answer. 0.89 what? One more. 894? It should be, yes, 0.894. That's joules per gram degrees Celsius, because that's what we have here. Let's put the units in now. I just put the numbers in there. This is joules, this is grams, and that's degrees Celsius. Okay, so this is our specific heat capacity that we calculated for our unknown metal. Now we need to figure out what it is by comparing it to a table of knowns. So 0.894, and I gave you that table here. Oh, look, it's already circled because I was talking about it earlier. It's aluminum. 0.897, we calculated 0.894. So it's aluminum. So in this case, we followed the sign conventions. I was making sure that we were keeping track of T final minus T initial, and I was using Q of the calorimeter is equal to minus Q of the reaction. But remember that the positive and negative sign, that's just a convention that tells you the flow of energy. We also know that the energy is being transferred from the block to the water without any loss. Energy is transferred from the block to the water without loss. So we know what that amount of energy is. In this case, it was 1631.8 joules. That's how much energy is involved in the transfer from the block to the water. So we could have also solved this same problem by just saying that whatever happens in the calorimeter, that amount of energy is the same as the amount of energy that's happening in the block without having to worry about the direction of flow. Just to show you, the math like that would look like this. The calorimeter side, we know is 50 grams times the specific heat, 4.184 joules per gram degrees Celsius. And that change in temperature was 7.8 degrees. And we're going to set that equal to whatever is happening in the block. The block was 25 grams and some X specific heat capacity, X joules per gram degrees Celsius. And its change in temperature was 72.9. Now notice I'm leaving the sign off because now I'm just saying, I know that the amount of energy is the same. So I don't care about the sign convention anymore. I just want to solve for X. And it works the same way, okay? And in fact, if for a problem like this, you don't really need to pay attention to the sign convention because specific heat capacity is always going to be a positive value. If we solve for X, X is now going to be equal to, here, let's keep the color coding the same for you. X is going to be equal to 50 grams, 4.184, 7.8 degrees Celsius, divided by now the two knowns that we had here from the block, 25 grams and 72.9 degrees Celsius. And you should get the same answer, okay? There's always more than one way to do these problems, but if you do it this way, you do have to be very mindful of what the sign's going to be in the end and when you need to pay attention to the sign. All right, we're going to start talking about the next topic and then we're going to finish it up on Friday. So we're still going to be talking about Q and we're still going to talk about delta H, but now we're going to put that into the context of describing more types of delta H of reactions, right? Delta H of reaction, remember, is a general term. And we talked about the delta H of dissolution. That's for dissolving 1 mole of something. Dissolving 1 mole. There's we can calculate the delta H of combustion if we wanted to. That would be the energy related to combusting 1 mole of material. Combustion of 1 mole of material. We can talk about the delta H of fusion, which is 1 mole of material being fused. And what does fused mean? In this case, it's going to be 1 mole of material that goes from the liquid state into the solid state. And actually, it can go either way. Which direction it goes in, as you'll see, is just a sign usage. Is it going Positive, it's going out of the system. Negative, it's going into this. Sorry, vice versa. Negative, it's going out of the system. Positive, it's going into the system. We can also describe a delta H of vaporization. That's going to be for 1 mole of material that goes between the liquid and the gaseous state. And there's others as well, okay? But they all go under the umbrella of delta H of reaction. We're just going to specify. Oh, there's one more I'll tell you about, since I'm defining these, because we're going to be using these in the next couple of lectures. Delta H of formation is one more. That's going to be a reaction. It's a combination reaction. So it's forming 1 mole of material from elements as they're found in their natural state. And I'll be redefining these when we use them, but we're going to be using delta H of formation later on in the lectures. We're going to be using delta H of vaporization and fusion in this next current discussion here. All right, so we're going to look at this heating curve. And in a heating curve, even though it's not a curve, it's a bunch of straight lines, but we still call it a curve. And this is an example taken right out of the textbook. And in the textbook, they talk about taking ice, so solid H2O, and we're going to start with solid H2O at a temperature of negative 18 degrees Celsius. And we're going to raise it and keep raising it until it turns into a vapor and goes off into the gas state. And water is a great example for this, because we all have a pretty good idea of what the boiling point and the freezing point of water is under general atmospheric conditions, right? In degrees Celsius, what's the freezing point of water? 0 degrees Celsius. What's the melting point of water? It's also 0 degrees Celsius, right? Melting is the same as freezing. It's just going in the opposite direction, okay? And we're going to be talking about that, okay? The melting point and the freezing point are the same. 0 degrees Celsius. What do you call 100 degrees Celsius? What happens there? It's the boiling point. But boiling point, what happens at the boiling point? You go from the liquid phase to the gas phase. What else happens at 100 degrees Celsius? Condensation, right? Going in reverse. If you're starting hotter and you start cooling things down, when you get to 100 degrees Celsius, that's the temperature where where water condenses from the gas phase back into the liquid. So this is also the condensation point. Condensation is when we go from gas back into the liquid, okay? So don't just think of these things in one way, all right? They can go in reverse. Now, in this example, though, we are going in one direction. We are heating up. So on the x-axis, we're constantly adding energy. So if we start at minus 18 degrees Celsius, okay, if I zoom in here, there's a small part of this curve. Believe it or not, you can get colder. Ice can get colder than 0 degrees Celsius, okay? 0 degrees Celsius happens to be the point where actually the solid is in equilibrium with the liquid. Now, it's a little different concept, all right? But if we're starting at minus 18 degrees Celsius and we start to add energy to the solid H2O, it will rise in temperature. And we can define that rise of temperature the way that we have been doing it. Let's call this region 1 of our curve. Region 1, we're going from minus 18 degrees, minus 18 degrees Celsius up to 0 degrees Celsius. And you can see that as you're adding energy, the temperature of the solid H2O is getting higher. But something very, very interesting happens when we get to this point here. So let's call this section 2 in red. In section 2, what's happening? You're told right here. This is the freezing point. This is the melting point. And I told you, it's when the two phases are in equilibrium. So what we have is the solid phase is transitioning into the liquid phase. When that happens, we're still adding energy, okay? We haven't stopped. As long as we're going from left to right on the x-axis, we're adding energy to this system. But look what happens at phase 2 when we're doing this phase transition. The temperature doesn't change. But why is that? Because look what happens here. Once we get to this next phase here, the temperature starts to go up again, right? This green line, phase 3. But what phase are we in here on this green line, do you suppose? Going from 0 to 100 degrees. Is it the solid, the liquid, or the gas phase? It's liquid. So this is all liquid. When it's all liquid, you add energy to it and it gets warmer. I can't write it because it's too small, but the blue section, right? When it was all solid at minus 18 degrees and you add energy to it, the temperature increases. Remember, energy and temperature, okay? In the red phase, when we're transitioning between phases, we're still adding energy, but the temperature stays the same. Why? Why do you think the temperature is changing the same?
Water takes a lot of energy and it has big specific.
What did we talk about up here? Slide whiplash time. Internal energy of the system. All right. You guys have been talking about the kinetic energy, the energy of motion, the molecules moving away from each other and whatnot. But there's still potential energy that's stored in the bonds as well. There's vibrational energy and there's rotational energy of the molecules as well. All of that gets factored in. Okay. So it's because of all those things added together, what's happening, the energy that you're adding to the system in the red section, that's just going into the conversion of the solid phase to the liquid phase. So that's why the temperature isn't increasing, because that energy is going into overcoming the potential energy that's stored in those bonds, or the other potential energy that might be stored in like the lattice, the solid lattice, separating it into the liquid. Okay. The same thing is going to happen here when we get to 100 degrees Celsius. At 100 degrees Celsius, we're continuing to add energy to the system, and now we're transitioning from the liquid phase into the gas phase. So we have another phase change here. And once again, the temperature is not going to increase because now all the energy is going into the phase change. So this one I can write more, but the same thing's happening in the red phase. When we start up here, this is all liquid. And when we end, this is all gas. If we're anywhere in between liquid and gas in that exchange, that's when the temperature is not going to increase, because now the energy that we're adding is going into the phase transition. It's not until we get to the all gas that now, as we continue to add energy, now the temperature starts to increase again.